Most robotics textbooks are written at an advanced level for graduate students and focus heavily on mathematics and theory. There's a deficit of affordable and engaging options for undergraduates, as most of the existing textbooks are over their heads. Engineering faculty at Middle Tennessee State University have filled the gap by developing an interactive virtual textbook for undergraduate students, focusing on both mathematical theory and practical industry-informed applications. The textbook includes embedded videos, quizzes, H5P media, as well as printable text, slide decks, and programming code examples. This presentation will explain the open access textbook and its relevance to both academia and industry, and share student feedback from piloting the resource in spring 2025. The goal of this talk is to raise awareness of the initial problem and improve the cost, quality, accessibility, and applicability of robotics instruction to undergraduates studying engineering as part of a 4-year Bachelor of Science program. After watching this video, you will be able to find the OER textbook for Robotics and Controls Engineering, understand how to use the book for an undergraduate robotics course, identify the components of an interactive textbook versus a conventional one, and identify the impacts of the materials on student course perception. Part 1 of the book covers material for undergraduate robotics course instruction, while Part 2 is relevant to student clubs developing small robots for competition, and Part 3 covers material for an undergraduate controls course. Each part of the book was written by a different instructor with relevant expertise. This presentation will focus on the first part of the book, which is the most interactive and widely applicable for robotics course instruction. I will explain each chapter in Part 1 of the open access book and its relevance to both academia and industry. I will then provide details on both the application and theory content and explain how to use the book in either synchronous or asynchronous learning formats. Finally, I will highlight the characteristics that make this book engaging and interactive with H5P content and share student feedback from piloting the resource in spring 2025. Chapter 1 covers the basics of industrial robots, including types of robots and joints, applications of robots, how to select a robot for a job, and CAD modeling and simulation. Much of the information in this chapter is focused on skills students will need if working in the robotics industry and is based on techniques I developed during my time as an engineer in this field. Special features of these chapters include video, text, and embedded interactive quizzes, focusing on the ties between mathematical theory and industrial applications. Instructors can assign students to watch the videos for asynchronous learning or cover the material in class and have students use the book as supplemental instruction. Some of the videos have a question pop up on the screen where these little dots are, and that is where the students can check their understanding. So the student can select their answers, check, and if they got it right, they can continue. If they got it wrong, they will have a chance to retry. For those who would rather watch the video without this, there is also a separate link to the video on YouTube where they can also view it with closed captions, play it at high speed, or skip to certain parts if they're strapped for time or looking for specific information. Towards the end of each subtopic, there is a quick quiz. So this allows students to check their understanding based on the text in the videos. So a student can click an answer and check it. If the answer is wrong, they can retry it, check again, and move on to the next question by clicking that arrow. Chapter 2 begins the traditional robotics math rigid body transforms. This includes both rotations and homogeneous transformation matrices, used for mapping the pose of a joint in one frame to that in another frame. So the rotations focus on orientation, mapping orientation of one frame to another frame, and going into different ways to express this, especially roll, pitch, yaw, which is the most commonly used in robotics and aviation. The next section, homogeneous transformations, includes a position change as well as a rotation change, and so it walks through the math for that as well as some examples. Chapter 3 gets into forward kinematics, which is mapping a robot's joint positions to its end effector position. So it walks through the different coordinate frames and axes of a robot, as well as instructions for how to find forward kinematics 3 different ways. First, the basic method, and then 2 additional methods, the Dinavitt-Hartenberg, which uses a standard formula for a transformation matrix and is used with only x and z coordinate axes, and then the product of exponentials method, which is a little bit more complicated, but can be easier to do in certain situations. So there's a helpful table because the math can get a little bit complicated, And then there are examples using standard industrial robots. Chapter 4 is the most complicated math chapter, covering inverse kinematics, Jacobians, and singularities, as well as simulation programming. So the inverse kinematics is the opposite of the forward kinematics. It maps the end effector position to the required joint positions. So these videos give some theory and examples on how to use that, and then gets into the Jacobian, which is a mathematical form of the derivative used to map end effector velocity to joint velocity or acceleration. So there are multiple methods and multiple examples so that students can choose whichever is the most applicable for their robot situation. It also covers applications of the Jacobian so that students know why they are learning this type of math. One of those specific applications is to identify robot singularities, which are an extremely dangerous position where the robot cannot solve where its joints are supposed to be in order to reach a specific tip position. So this is covered in all of these videos and examples so that students can be able to both visually identify and calculate those situations. Finally, a special feature of this chapter is programming examples, so that students will be able to simulate a robot in order to check the math that they derive. So these examples walk through an algebraic solution of how to derive that and then how to program that robot in MATLAB code, as well as a numerical solution and walking through that so that students will have two different methods in their toolbox of ways to simulate a robot, depending on the complexity of the robot and the way that its joints are set up. There's also a review of Newton's method for students who may not have had the mathematical background to understand the programming. Chapter 5 is another industry-oriented chapter based on my experience as a robot claw designer. Here, students learn about the 3 basic categories of end-of-arm tools, as well as applications and design principles. So the introduction basically just talks about the different parts of an end-of-arm tool and what the 3 basic kinds are. And then the next few sections go through the magnet tool, which is one standard type, some application examples, and how to calculate that kind of tool. And then the suction tools, which is a little bit more complicated, some additional examples for applications and calculations on that. And then finally, the gripper. So grippers actually have many, many different kinds. There are both hard robotic grippers and soft robotic grippers and so many different numbers of fingers that could be had, but the gripper end of arm tool example talks through the basics of a 2-finger parallel gripper so that students can have some of that foundational knowledge. Next, I will share student feedback from piloting this book in spring 2025. A primary goal of the book was to distill the advanced theory common to robotics and controls textbooks meant for graduate students into a simpler, more digestible format for undergrads. As evidenced by a survey given to the 30 students in the course, this goal was met. 72% of students favored the math-focused chapters over the application-focused chapters, and 80 to 90% of students said the book enhanced their understanding of rigid body transforms, forward kinematics, and inverse kinematics. One student said the book is very concise and to the point, without the extra fluff that can bog students down. While another shared, the chapters, while seemingly short, are easy to digest, don't have a lot of alienating jargon, and are well organized. And finally, another student shared that the book is easy access, easy to read, and easy to navigate. Feedback collected from students indicated that the #1 improvement would be to include slide decks in addition to the text and videos, which would facilitate learning in the event that a student did not have the time, internet bandwidth, or earbuds to watch a video. A secondary improvement suggested was to include MATLAB code examples to help students apply the theory learned in a simulation context. These suggestions were implemented for Chapter 4 of the book, which a quarter of students then listed as their favorite chapter, despite the fact that it contained the most challenging content. So these items will be included in a later revision of the text for future courses. You can access the book at this QR code. It is the author's hope that the book will bridge the gap between robotics theory and application and improve the cost, quality, accessibility, and applicability of robotics instruction to undergraduates studying engineering as part of a 4-year Bachelor of Science program.